Those of you at home, pause the video and copy. You'll also need out a periodic table. All right, yesterday, I hope you remember that I introduced you to how to calculate the mass of a compound, right? We call it molar mass. And it was very simply done by adding up the parts based on their masses on the periodic table. Add them up, get a molar mass, you're done. We took it a step further though, and we saw that we could also find a percent composition by dividing the total mass of each element by that molar mass, total mass, times 100 to find a percentage. We're going to use some of those skills today, but today we're going to go in a slightly more super chemistry direction, because the word mole it's a big word for us. This idea of the mole concept is going to be haunting you for several upcoming units. And while the word itself is really simple, there's an abstractness to some of it. So focus in so you're not one of the students that I lose. In chemistry, we're constantly having to deal with annoying numbers. Like, we already deal with the smallest thing that existed here, atoms. So if I were to tell you to tell me the size of an atom, the number that you'd have to give me would be extraordinarily small, which means there'd be a bunch of leading zeros, and it would be annoying to work with. On the flip side, if I were to ask you how many atoms are in this calculator, well, the number is extraordinarily high, because atoms are so small that you couldn't even fathom the amount of atoms it takes to build the samples of matter that you can see. So those numbers would be huge. So what happened is, a long time ago, there was a solution word created to make the numbers more gentle, the mole. In its simplest form, if I were to try to explain to you what a mole is, it's a made-up unit. It's totally made up in chemistry, but it's our counting unit. It's the way that we count elements on the table. Really, 1 mole of something is 1 square of it on the periodic table. So now, if I were to ask you, look at your table, if I were to ask you, what's the mass of a mole of nitrogen? Round it to a whole number. What is the mass of 1 mole of nitrogen? It's 14. Everyone find it, verify, because 1 square of nitrogen has a mass of 14. So 1 mole of nitrogen is 14. All right, well, what if instead the question was, what's the mass of half a mole of nitrogen? What would it be? It'd be 7. It'd be half of one of the squares, right? What about 2 moles of nitrogen? 28, 14 twice. The idea should be simple, all right? And then, so if someone says, hey, you know what I found out in nature today? I found me 10 moles of hydrogen. Well, you would know right away that, cool, that means he found 10 grams of hydrogen. Because if you look, a mole of hydrogen is rounds to 1. So that's moles in a nutshell. The reason it gets a little harder to think about is when you compare it to atoms. So we know that atoms are the smallest particles that exist, right? Protons, neutrons, electrons, we've done atoms. Avogadro. Have y'all heard of Avogadro's number before? Sometimes it's like a random trivia word that some of y'all have just heard before you meet me. Anyway, Avogadro is the scientist given credit for assigning a value to the number of atoms in 1 mole of anything. Now, I want you to look at Avogadro's number. It's the purple number there. Is that a really big number or a really small number? It's a huge number. Do you see how it's times 10 to the positive 23? It wants you to slide the decimal to the right 23 times, right? It's a huge number. And it's the number of atoms, right? There's so many atoms in any sample of anything. It's the number of atoms in 1 mole of anything. And it's that anything that throws you. So refocus. We're using the word mole here, kind of the way you use the word dozen. When I say a dozen, what number do you think of? Do you see how you said 12 without asking me, well, a dozen of what? Because it doesn't matter. A dozen is always 12. Just like a mole is always Avogadro's number of atoms, no matter what. Now, the word dozen connecting to 12, the samples can still be way different though, right? Like if I had a dozen cotton balls over here and I had a dozen semi-trucks over there, well, there's 12 of each, but the samples are dramatically different, right? I could go pick up the 12 cotton balls, right? And I'm probably the only one in the room that could pick up the 12 trucks, but it's an acquired skill. So just because you use the word a dozen to describe two different things, they're both 12, but they're both different. So you've got to get your brain wrapped around it. Let me try to help you. Show y'all before I show them. What I've done is I've collected two samples of two elements. In this hand, I've got copper. And in this hand, I have lead. And what I did, I never know if y'all can hear me. Copper, lead. I went and collected exactly 1 mole of each of them. So how did I do that? How do I know that this is 1 mole of copper? So I took a big thing of copper, a bucket of copper to the scale. How many grams did I measure out to make it be 1 mole of copper? About, did you say 58? Copper, about 64, right? What are your numbers you're looking at? Copper, 64. Come on. They're making the video look bad. I'm not going to tell you who it is, but anyway. Yeah, I measured out 64 grams because that's how many grams is 1 mole because it's 1 square, right? So then what about the lead? I did the same thing for the lead. This is exactly 1 mole of lead. So what's the mass of the vial I'm holding? Oh, now you're scared to answer. 207. Lead is PB. All right, I'm going to record in 6th period next time. Lead is PB, so this one is about 207 grams, and they're both a mole. Which one's heavier, the copper or the lead? The lead, right? I mean, I just told you how I found them, right? The lead is heavier, it's 207-ish, all right? And this one's only around 65, 63-ish, all right? So let's talk about what they have in common and don't. They're different elements, so that's a different. They're different masses. This one's heavier than this one, right? This one's heavier. But what do they have in common that's the same? They're both a mole. They are both 1 mole. Hey, who's got more atoms? Which vial contains more atoms? They contain the same. Because 1 mole of anything contains Avogadro's number of atoms. And there's the abstractness that you're going to have to get to seep into your bread. So one more time. Your bread, your brain, your bread. Anyway, so one more time. They're different elements with different masses, but they're both 1 mole, therefore they're both exactly Avogadro's number. Another way that I can demonstrate this equality that I'm talking about is like this. Because what you'll notice is that this screen is the exact same equality. It says that 1 mole of something is the grams on the periodic table of that thing, just like 1 mole is equal to Avogadro's number. Go ahead and copy that down, please. It'll be the last direct copy I have you do. And while I absolutely need you to understand the concept that I've spent the first 10 minutes on, the other thing I want you to be able to do today is convert between units. Do you remember back in Unit 1 when I asked you how to figure out how many seconds old you were? And I taught you how to use dimensional analysis to do that. It was a grid, an organized grid to solve complex problems. We're going back to that. Because I need you to be good at it because we have a much harder math coming up next month. So we want to get really good at dimensional analysis again. So what I want you to do is for me to say, okay, well, if I give you 100 grams of something, Can you tell me how many atoms it is? A real simple conversion. Let's do a handful of them. You ready? Don't write down that black stuff that showed up. That's for me, not you. But do write this down. Let's say that we had 20.3 moles. Aspen's in play. Let's go mess with some people. Let's go over to cluster 5, seat 2. Hey, 5-2, what is your favorite element? Nitrogen? Yeah, this is the second nitrogen today. Y'all really like nitrogen. Okay. Hey, he did this, not me. What's interesting about nitrogen just existing there by himself? It needs a 2, right? Nitrogen's diatomic. That is not a part of this lesson. Again, that's his fault. But yeah, N2, Brinkelhoff. Anyway, if I have 20.3 moles of nitrogen, I want to know how many atoms is that. Now, those of y'all that are good at math, you can already see a logical way to solve that without doing what I'm about to show you. The reason I want you to do what I'm about to show you, though, is we have a thing called stoichiometry waiting for us in the near future, and you need to be good at my grids to survive stoichiometry because you won't be able to rationalize it. So, do my steps. Here we go. Let's convert this to this of nitrogen. Here's what I do. I'm going to take the number that they give me to start off a dimensional analysis grid. There's the phrase that was given. Ow. I'm going to put whatever I'm trying to get to in the neighbor square right next to them. In this problem, I'm trying to find atoms of nitrogen. Does anyone remember where the letters from this square come from? Oh, come on, September wasn't that long ago. It's a diagonal drag. I take the information from here, not the number, but I take the units and I drag it down to the diagonal. And this is the repetitive steps that we'll take on all of these. If you remember, whenever you've got two squares right over each other with no numbers, in dimensional analysis, they must equal each other. So if you had like a week on one, you could have 7 days in the other. They must be the same, which is what our conversion factors are for, right? The purple is the answer. So if you look at this top, what number should I put in that top square? No. Look. See the word atoms? So I go straight over here to the screen, and I find the word atoms, and it tells you the number, all right? So you find the unit, it tells you the number. Unit, number. Unit or unit, number. So we've got atoms in that square, right? Avogadro. My bottom square says moles. Look at the screen. Find moles. The number is 1. And now we have plugged. You'll notice that the mass of nitrogen did not show up at all, and that's because grams is not a part of the problem, right? Just follow the work. Now, if you've forgotten how to solve this, remember you multiply across the top and divide by the bottom. Be careful with your scientific value there. E stands for times 10, but don't put times 10. Make the E show up on the calculator. It's the secondary button of the button above the 7, secondary function rather. So hit the second button, and then the button above the 7, and the E will show up. Yesterday, we did not have sig figs affect us because molar mass and percent composition always go to 2 digits past. But Mole conversions, normal sig fig rules. So sandwiched zeros are significant. 3 sig figs, 3 sig figs. Anybody need me to come look at their calculator?
Say that louder. The second button. Say that out loud.
So it's the second button.
Yeah, say it right now.
Yeah, so there's no dividing. You multiply across the top and divide by the bottom.
All right, y'all. So I'm going to do that thing where I ask for favorite elements a couple more times. So right now, while I get the next problem ready, decide what you're going to answer so that it's a good answer. And let's do another problem. Let's go 300 grams. Let's go over to cluster 4 and talk to C1. Aspen. What's your favorite element, Aspen? She said hydrogen. Okay. Here, pick something that's not diatomic, though. What's your second favorite, not Brinkelhoff? Selenium. All right, there we go. I haven't had a selenium today. All right. If you have 300 grams of selenium, I want to know how many moles that is. So let's get this going together. Start with your entire given expression. So I'm going to start with 300 grams of selenium. Remember, the square next to him is what you're going to, which is moles. What units go down there? Grams, yeah, the diagonal drag. Just do the diagonal drag. Grams of selenium, don't drag the number. Very repetitive, except the steps. All right, here we go. Remember, you just match the unit with the screen over there, and it tells you the numbers. I see the word mole. I find the word mole. You find the number 1. But what about grams? What does the screen say that we need to do for grams? Yeah, for grams, it's the periodic table. All right, that didn't happen last time. But now the fact that we're doing selenium is a big deal. What's the molar mass of selenium? 78.97. And boom, we got it all filled in. Multiply across the top, divide by the bottom. Because there's amendments each year as isotopes change. Careful on your sig figs here. Anybody brave that wants to share what they think the real final answer is? Yeah, it's 4. 4 moles. Remember, zeros that end a number are not significant if there's no decimal shown. So there's only 1 sig fig, so I rounded. I mean, you probably got what, 3.7989, blah, blah, blah. I rounded it to 1/6. All right, let's draw more cards this time and get some real math help. Sounds fun. All right, here we go, y'all. Let's start with 0.4 moles. Let's go over to cluster 5, seat 1. Hey, Aspen, what's your favorite element? Say again. Tungsten. Tungsten's a lot of fun. Y'all know that tungsten was W? I know, y'all suck. Okay. But hey, let's marry somebody to tungsten. That'll be more fun. Let's go to cluster 1, seat 2. Who would you like tungsten to marry? Uranium. All right. So let's write it like this. All right. I don't think I've ever written that compound on a whiteboard in my 18 years, so congrats on creating a true monster. If I have that many moles of ditungsten uranide, still making things up, I want to know how many grams is that. All right, let's get this set up. Start with my value here, of course. The given expression always starts your dimensional analysis grid. All right, now let's go get some help. Let's go over to cluster 5. We are keep trying cluster 5. Seat 5, but Aspen, what units will go in that square? Just units. Grams, yeah. What you want? We want grams. So we're converting to grams. Let's go over to cluster 1, seat 1, Aspen. What units go in that square? Yep, the diagonal. We drug the diagonal. All right, and you can pass the bird. All right, let's go over cluster 1, seat 1. Did I just do 4 aces in a row? Woo! Be a good day. Hey, Aspen, what number goes in the bottom square? The word mole is the conversion factor 1 from the screen. And you can pass the bird. Hey, what's going to happen up there, though? What's the word for, you're right, but what's the phrase? We're not just going to find it, it's grams, so it's periodic table. But what is that number going to really be called vocab? The molar mass, because we learned that yesterday. Woo! Yeah, because we're adding up the mass of a compound. The square for the PT will represent the compound that's there. That's why we fill these squares in this order. W2U. Now, you can make your list like we did yesterday, or you could go a bit more honors on it, and you can do most of it in your head, right? It's 2 W's and a U. So look it up, because I'm going to draw another card. Look it up. It's W plus U, which sounds ridiculous to say. Find the molar mass of that square. It's very funny. I like that comment. Let's go over to cluster 2 because they are so brilliant, and we will get an answer from seat 6. 2-6. Do you have a molar mass for that square? W plus U. Tungsten is element 74. Uranium is element 92. Hey, I'm teaching.
Oh, you're still teaching?
I am still totally doing it.
Okay.
You're on speaker. Say hi. Say hi, 8th period. Hey, everyone, say hi, Mrs. Cummings. Your nephew's in here too. I love you. All right, bye. Did you get a number? Oh, no, it's not big enough. What's the number? Yeah, 605.71. All right. W plus W plus U. And now, hooray, we can solve. So solve. Multiply across the top and divide, and you're good to go. I didn't ask anything. I believe you. No, he doesn't. No, that didn't count for his. It was a card draw. I get, if you sig fig it, I get 240. Right? There's only 2 sig figs. Ending zeros are significant if there's a visible decimal. So my calculator said 242 point numbers. How are y'all feeling about this?
Oh, wait, I see what you did.
I just rounded to 2 sig figs. Yeah? Think you can do one by yourself? Hey, before we do this last one, I have good news. Tomorrow's lab is a chew gum lab. I've got sugar to feed you to end your week. So, hooray. Anyway, let's do one more. All right, y'all. Let's go 8.09 E24. 8.09 E24. And we're going to do atoms. And let's go mess around again. Cluster 2, seat 2. Hey, 2, 2. You got a favorite element? Say it again. Xenon. She went all noble gas on me. All right, here. I'm going to throw a little twist in this next question. Let's go to cluster 6, seat 5. Aspen, do you have a favorite polyatomic ion? No. Say it.
Thiocyanate.
Thiocyanate?
Yes.
Or are you going? Oh, okay. Sorry, I thought you were going. Let's go with xenon. Let's do this. There we go. I want to know if you have that many atoms of another totally made up compound. How many grams? Go. You've got this. Exact same steps. I believe in you. You get stuck, call me over.
Yes.
If this is a dumb question, if this is a dumb
Just ask
question,
it. You're good.
it's Isabel's question. And if it's a smart question, it's my question. So do you multiply the 3 masses inside of the parentheses?
Yeah. Remember, it distributes. So in this compound, there's 3 sulfurs, 3 carbons, and 3 nitrogens. I'm going to start trickling some work up here, but you're welcome to ignore me if you're not stuck. 8.09 E24.
No.
Take a glance at my work to make sure you're on the right track as you keep going. Can anybody verify this number? Did anyone else get this number already? Okay, beautiful. Keep working. I just want to make sure because I've been known to slip a decimal the same way y'all do. Now's a good time to ask a question. If you don't know where one of, keep working if you're working. But if you're stuck and you have a question, ask it out loud. Anyone confused on any of my incomplete work here? About both of these? Which number? The 305? So since grams is in the square, it's periodic table. Do you agree? So periodic table is based off that 3. So therefore, this is 1 xenon, 3 sulfurs, 3 carbons, and 3 nitrogens. I just added up those masses. Xenon plus S 3 times, C 3 times, N 3 times is that number.
You're wrong. I'm right. Oh my god. I'm so wrong.
3.
Oh.
I'm listening. Yeah. This square is the molar mass of that compound.
Okay, but that was because you were texting. Oh my god. Oh my goodness. Look at that. Look what's wrong. I got it right. I got it right too, Nolan. You know who got it wrong? Oh my goodness. I'm dropping.
Do you always do that?
Why don't you watch my videos? You know, if you were a fan.
She's a lot.